Greetings, calculus students. As you probably guessed, I'm not here today. That is, not here in the classroom, but I am here on this video. Now, in all seriousness, what's most important is that you're here. And today needs to be a day of learning. In fact, it's the third day of our discussion on limits. And I wish I could be here because on this third day, it gives you an opportunity to practice some limits, to kind of summarize some ideas. Really, the goal of today is that you leave feeling like you understand limits. So what I want you to do is to very carefully go through the lesson that I have prepared. You're going to use this video. You're also going to use a form. You're going to kind of have both the digital form and this video sort of working at the same time. But be careful that you don't just watch the entire video, and be careful that you don't just fill out the form, but rather pay attention because you're going to pause the video, you're going to go to the form, come back to the video, and eventually have your day of learning. So what I want you to do now is open up that form. There's a link to a digital form. You can sign in. And after you do that, you're going to see the first thing is to take a look at these two warm-up problems. So once you sign into the digital form, you're going to see these two warm-up problems. Go ahead and put these warm-up problems in your notes. They're actually two problems that you're going to want to try. You're going to want to try to figure out. Remember, that's the whole point of today. Now, this first one, I want you to try to figure it out with an analytical method. That means no graphing calculator. So how would you find this limit analytically? The second one over here, you can do it any way you want. I'm actually kind of curious what would be your initial response, your initial thought. What method would you use to find that limit? Okay, so what you're going to want to do is try these two limits, then submit your answer and explanation as required in the form. And so at this time, you also want to pause the video. Now, you should only be watching the next part of this video if you've already submitted your two limits, because what I'm going to do now is go over, yes, we're going to go over how you would find these limits, exactly what we would have done in the classroom, of course. Now, for this first limit, actually, I am curious, did you first think about just plugging in 5? That may be arguably the simplest analytical method where you're basically using a substitution method. Now, if you're like, Miss Naylor, I didn't actually do that. Well, you need to. It needs to always be your first thought. Now, it turns out that when you plug in 5, you get 0 over 0, which is actually meaningless. We call that the indeterminate form. And so it does mean that you have to do something else. And that something else very well should be factoring. Now, I did give you a nice hint, didn't I? So if you did factoring, nice job. And it should factor into x minus 5, x minus 5. Now, the cool thing about factoring is that it actually, we actually are able to cancel the problem. We're able to cancel the 0 in the numerator and in the denominator. In other words, we're able to cancel the indeterminate. And we're only left with x minus 5. Well, you're now all clear to substitute. And of course, when you substitute, you get 5 minus 5, which is 0. That means that the limit as x approaches 5 of this function is 0. How about our second limit over here? Now, if you used a substitution method, you might say that that's all you had to do. Are you allowed to substitute in 0? Do you get something that is determined, that is a value? Well, you do. You straight up get 2 over negative 2. And 2 over negative 2, well, that's always equal to negative 1. Now, honestly, that's as simple as that problem can get, but I understand that some of you may have used a graphing method, and even if you didn't use a graphing method, it's worth discussing, you're going to get a rational graph, and rational graphs have asymptotes. Just a little bit of a footnote here. The asymptote actually doesn't matter for this problem, but we do get branches. So you get a graph that has a branch, and, well, you should have got another branch. The truth is, all that really matters in this problem is where x is getting close to 0. And this gold dot right here is exactly where x is getting close to 0. And all we got to do is ask ourselves, what's the intended height? Well, the intended height would be the y value, and the y value at that point is actually -1. You see, all that's really happening in this problem graphically is that there is a point, 0, -1, and that would be my intended height. In fact, it's my actual height. What I'd like you to do now is kick back a little bit and watch this short little summary video discussing limits.
Now you have some idea of what a limit is, and we need to talk about when does a limit exist. To illustrate my point before we get started, let's set up an example. Let's say you and a friend are going to meet for dinner, and you're meeting at a diner that's centrally located between the two of you. If you live east of the diner, and your friend lives west of the diner, and you both want to drive to meet there, ideally, the roads which lead to the diner will lead you to the same place. If you travel towards the diner from the right, or east, and they travel towards the diner from the left, you should meet up in the same place. Mathematically, this is basically what a limit is. A limit exists if you travel along a function from the left side and from the right side towards some specific value of x. As long as that function meets in the middle, as long as you arrive at the diner, as long as the heights from the right and the left are the same, then the limit exists. Now it's time to get down to the brass tacks and look at this mathematically. Take a look at the graph of this function f of x. Visually you can see that it's got a break in it at x equals 4. So, if we travel towards 4 from the right, we will arrive at a height of 2. However, if you travel towards 4 from the left, you will arrive at a height of 1. This means that no limit exists for f at x equals 4. Let's go back to our diner metaphor for just a second. Notice that as I'm traveling along the road from the right, I end up at a height of 2. But if you travel along the road from the left, you end up at a height of 1. These heights don't match. We won't both arrive at the diner, and no limit exists. We call the height at which we arrive from the right-hand limit of f of x, as x approaches 4 from the right. And we denote this with a little plus sign in our limit symbol. Our height that we arrive at from the left is called the left-hand limit of f of x, as x approaches 4, and it is denoted with a little negative symbol. Mathematically, in order for a limit to exist, both the right and the left-hand limits must be equal. Now let's change this function just a little bit. This new function, we'll call g of x, does possess a limit. Can you see why that's the case? It's because the function no longer has a break at 4. Now, there's something to be said here. The previous function did not have a limit at 4. It did have a limit at many other points. For example, a limit existed at 1, at 2, at 5, at 0. All these x values showed locations where the graph did not break. In essence, a graph will not possess a limit if it breaks at the given x value. That's why our new function does possess a limit at x equals 4. Now, let's go back to our diner example one last time. Let's say we're traveling towards the diner. We both arrive at the same location, but the diner isn't there. Maybe it's caught fire or something. Does that mean the limit doesn't exist? The truth is, the limit will exist even if the diner's not there, because you still arrived at the same place. In other words, mathematically, a limit can still exist if your destination is a hole in the graph, because it doesn't matter whether or not the point is actually there. What matters is that you arrived at that point coming from the right side and the left side. In conclusion, a limit exists on a graph if you arrive at the same height coming from both the right and the left side of the given x value.
Did you hear that? That's it. That's the holy grail that we've been looking for. That's how we know if a limit exists. Let's just sit on this slide for a second. Isn't this what we've actually been doing since the beginning of limits? We've been looking from the left, we've been looking from the right, and when those two limits are the same, then we can say that the limit exists. Now, this would be worth considering using some notation. Yeah, in your notes, let's see if we can write this statement that the limit as x approaches c of f of x exists when blank equals blank. Now what I want you to do, just pause for a second, write this in your notes, but even as important, I want you to see if you can fill in these blanks. Ready? We're going to fill it in, so pause if you haven't thought about it yet. It's as simple as saying with notation that the limit as x approaches c from the left, so of course that would be with a little negative sign, of f of x. It always has to be the limit of a function, so we need to have that f of x symbol there, but that limit is going to equal, that would have to equal the limit as x approaches c from the right of f of x. Plain and simple, when the left-hand limit is equal to the right-hand limit, well, that's when the overall limit as x approaches c is going to exist. All right, well, next on our little journey today, you're going to analyze various limit statements about this graph. Now, hopefully you didn't put your notes away because you're going to want to get a copy of this graph. Just take your time, make a little sketch of this graph, and what you're going to do is you're going to have a series of limit questions related to the significant places along this graph. So again, jot it down in your notes, and then remember that digital form. Well, once you're done making a copy of this graph, go back to that digital form and get to the next section. You're going to have some limit questions. Okay, it'll take you a little bit of time. Make sure you think through them, talk about them with your friends. See if you can get those limit questions right. All right, if you've made it to this part of the video, then you have finished the various limit questions on that graph, and you're ready for our last little nugget of learning. I'm going to talk to you about something called the greatest integer function. Now, the truth is, this is honestly just a function. You could have actually talked about it in Algebra 1. Usually we don't because there's just so much to do. But the reason we're talking about it today in calculus is because once we understand the greatest integer function, there's some pretty cool limit questions that you can do. So what is the greatest integer function? Well, first off, it's with notation defined or written like this, and often abbreviated int of x. And either way, if you would read this, you would read the greatest integer that is not greater than x. Now, what was that again? That's kind of a mouthful. Well, the greatest integer function, what it does is it outputs the greatest integer that's not greater than x. Let's just try a little bit of input-output for a moment. If I input 2.2 into the greatest integer function, what I need to output would be the greatest integer that's not greater than 2.2. What number, or what is the greatest number that's not greater than 2.2? Well, it would be the number 2. How about the greatest integer that is not greater than 1.9? Again, we're looking for a number. It's the greatest number. It's an integer, but it's not going to be greater than 1.9. Now, it can't be 2 because that is greater than 1.9. So that's right, it would be the number 1. Now, sometimes students begin to think or realize that it's kind of like we're just rounding down. Well, that's actually true. That's actually true until you get to perhaps the greatest integer that's not greater than 5. The greatest integer that's not greater than 5 is 5. 5's not greater than 5. It's equal. So it does fit the definition. What happens if I want to find the greatest integer that's not greater than 0.33? The greatest integer that's not greater than 0.33. That's right, it would be 0. And finally, what if I wanted to do a negative? Now here's where you want to be careful when you think about rounding down, because, well, what does that mean for a negative number? The greatest integer that's not greater than negative 1.8, okay, it would have to be negative 2, okay, because that's definitely less than negative 1.8, and it's the closest one. So again, it fits the definition. Now, what's this got to do with limits? We're getting there, but we need a graph. So what we're going to do is we're going to graph the greatest integer function. And what you want to understand is that this is the graph of the greatest integer function today, tomorrow, yesterday. This is the graph all the time. And it's really just a matter of thinking about input and output. So let me help you think about some input and output. We kind of did it here with that decimal of 0.33. And you realize that every decimal that is, well, in that sort of category of 0.33, like maybe a half and 3/4 and maybe 7/8, every one of those is going to output a 0. And so we end up with our graph kind of starting on the x-axis until I get to the number 1, which ends up being an open circle. Because what happens when I get to the number 1? Well, I literally would jump to the next y value, to the next integer. So 1.1, 1.2, 1.3, 1.4, all the way up to 1.9 until I get to 2. And what happens when you get to 2? That's right, it's going to jump to the next integer. And so what's happening here is every output is an integer, but it's the greatest integer that's not greater than, well, than the value that we're on. Okay, so we have, actually what we're creating here is called a step function. And a step function literally steps between y values. Now it works the same with the negatives. It works the same with the negatives, but we want to kind of keep track of where the open circle is, where the closed circle is. So it would look like this. I'm sort of adding to my graph a little bit as we go, but that'll be enough of that step function. Okay, ready to do a couple limit questions on our greatest integer function? How about the limit as x approaches 1 from the left of our greatest integer function? So the limit as x approaches 1 from the left. Do you know what step you're on? You're approaching 1 from the left. You're down on this step. And so your intended height, the whole time you're approaching 1, your intended height is 0. Okay, now be careful. That's, of course, the intended height. We realize that when we actually reach the number 1, right here, that we don't actually have a value, but that's okay. We're just intending to reach the number 1. How about the limit as x approaches 1 with a little plus sign from the right? So now we're approaching 1 from the right. Do you know what step you're on? What's your intended height as you're approaching the number 1? What's your intended height? Well, the whole time your height is 1. So how about the overall, sometimes called general limit, as x approaches 1 of f of x? How about the overall general limit? Sound a little bit like that summary slide from earlier in the lesson? Doesn't the left limit have to equal the right-hand limit for there to be a general limit? That is correct, and that does not happen in this problem. So the limit does not exist. There is no limit as x approaches 1. There is no general limit. All right, and you could do this again with another x value. You'll find out that it's a very similar idea, and you'll get to do that in the assignment. Speaking of the assignment, that would be the next order of business. All right, now you're going to have a work period tomorrow, but certainly encourage you to get started. Till then, bring some sunshine to someone's day, and I hope that this little lesson brought some to your day.